Hello. Today I'll be going over how to do a complex rollup analysis in MagicDraw. The example we're looking at here is a reliability rollup showing the total system reliability, and this can be calculated in a couple of different ways. So one way to calculate reliability is in series, which means if one part fails, then the whole chain fails. This is shown by parts 1, 2, and 3, which you can see add up in series to give the total reliability of part 4. Meaning in order to get the reliability of part 4, you simply take the product of 1, 2, and 3. The other way to calculate reliability is in parallel, which means if all parts fail, then the system fails. To calculate this, you need to take the complement of the reliabilities, take that product, and then take the complement of that result, as you can see by the equation in this note here. Now, when it comes to taking your total system rollup, there's a couple ways that you could do this. One is as shown on the diagram below by using constraint properties to individually pick what parts get rolled up either in series or in parallel, and then draw the binding connectors manually to give a very precise rollup based on your particular system. The other way to do a total system rollup is by applying a rollup pattern, which you could do by right-clicking your top-level block, going to Tools, and applying a rollup pattern from the list of available patterns in your model. MagicDraw gives you cost, mass, and power out of the box, which are all simple sums. And then you can define your own, such as this series reliability rollup, which I will get into in the second portion of this video. But for now, let's walk through this first method of using constraint properties. So we're going to walk through how we set this up step by step, beginning with adding a new block to this diagram and adding that into our parametric diagram below. So to start, let's add a new block to our model. We'll just call this part 7. And we're going to give that a value property called reliability. That's going to be typed by real. And let's give that a value of, say, 0.92. Now we could drag and drop this onto our BDD. We could say that part 6 has a directed composition to this, right? And now that's going to define our part property. And from here, let's go into our parametric diagram and add this into our total system rollup. So we could just drag and drop this block onto the diagram, right-click to display the value property, and then we'll go ahead and just give that part property a name. All right, and with this done, next we can add our constraint property. But before we do that, I'll show you how to create the constraint blocks, which are used to type these constraint properties. So in our containment tree, you can see we have a couple of constraint blocks, one for our parallel product and one for series. I'm going to walk through how to create one of these. So simply add a new constraint block. I'll call this series 2. And this will essentially be identical to this series product block. I'm just walking through how to create this for the sake of this example. So I'll expand this and let's create a couple of parameters. We need one for our inputs, we could just call that in, and one for our outputs, which we can call out. Now it's important that on the input parameter, we set the multiplicity to multi-valued, which is just this asterisk symbol. And that's going to allow us to take multiple inputs. So this is a very important step in the process. Make sure you have that set to multiple. And lastly, let's add our constraint. So in the specification window of your opaque expression, let's go to body and language. And in this case, we're going to use Groovy, although there's a number of languages you could choose from here. In order to make a Groovy script, what we need to first do is figure out the size of our input array. So we're going to create a variable, let's just call that a, equals to our input dot size. And we actually want the size -1. The reason for this is because we're going to define a for loop that goes through our input array. And when Groovy executes loops, it always starts the array at an index of 0. In order to accommodate that, we are going to start at 0 by subtracting 1 from our total size. Right, next we're going to say out equals 1. So we set this output to 1 initially because as we iterate through our input array, what we're going to do is start with a starting value of, say, 1, and multiply that by the first value in our array, which would be our first reliability in our input array. We are then going to take that result and multiply it by the second value in our array, and so on. So now for the for loop itself, we are going to say for I in 0 to a, where a is 1 less than our size of our input array, then we want to do out equals to out times in. Then we're going to close the loop, and that's all there is to it for setting up the Groovy script. Hit OK, close. So let's drag and drop a constraint property onto the diagram. We'll call this G times DE. And we're going to type this by that new constraint block that we just made. We're going to show the parameters. I like to put the output on the right and the input on the left, but you can arrange these however you like. And now we're going to connect these up. So draw a binding connector to your input. We're going to take the output from this parallel calculation for 4 and 5 and bring that into here. So I'm going to get rid of this binding connector. Just going to add a new part property as to kind of take this output from our parallel product and then roll it into our new input. So we'll just call that DE. From there, we can wire this up. All right, and with that all connected, we can now run this new simulation. And you can see if we change this value here, we have it at 0.92 now. Let's make that pretty low. Let's make it like a 0.75. You can see that's going to affect our overall system reliability. And I'll just bring that back up to, let's make it like a 9.6 or something like that. For the parallel product, it works the same way, except the formula is slightly different. If you would like to copy and paste these formulas rather than type them yourselves, they are available on our company website. Simply search modelworksllc.com, and then you'll see a link at the bottom of our page to our GitHub, where you can find the parallel and series product scripts available to simply copy and paste. So that covers the first approach of how to use these constraint properties to define your total system rollup. We will now get into the second approach of how to apply a rollup pattern. So I'm going to collapse some of these, do a quick save. So next, let's take a look at what a rollup pattern looks like. So I have this BDD here for my rollup patterns. And you can see we have a series reliability block here that is also stereotyped by this pattern stereotype. Now that's really important because when you add a block to your model, if you do your tools, apply rollup pattern, and click this drop-down menu, the only blocks that are going to show up here are ones that have that pattern stereotype. So once you have that pattern stereotype applied, there's a few other things you need to do. One, you need to have your constraint property, and we'll look at that in more detail on the parametric diagram tied to this block. Then you also need to have your values. So we have two values here. One is REL. That is the reliability of the part itself, which we have a default value of 1. And then there's your total reliability, and that backslash there shows that it is a derived property. As you can see in the properties window, is derive is checked true. And that basically means that this property is going to get calculated in our parametric diagram. And then the other important step here is that we have this association from the block to itself. And there's a few important things that you want to put here. One is this union. So if you click on your association, make sure that you have all selected for properties and then type union. You want to make sure that isDerived union is true. And then the other thing you want to check is your multiplicity. And for the roll of the series, you want to make sure that that is set to multi-valued by this asterisk. So if you don't have those set right, you can run into some errors when you simulate this. So make sure that you have those set. And then you could get into your parametric diagram. So we're going to open that up here. And you can see we have a few things going on. I'll expand this in the containment tree to show you what we have in here. So first you have your constraint property, and that is typed by the series sum, just as we were looking at earlier. You also have a few value properties in here. So one is your total reliability. So that's the thing that we are trying to calculate. And to calculate that, we multiply the reliability of the part itself by the total reliability of each of its children elements. And that comes from that part property, which we saw on the last diagram, sub-reliability. And those both get connected up to our constraint property as shown to complete our rollup pattern. Now let's take a look at how that gets applied. If we go back to our system reliability diagram, right-click on that top level block and go to Tools, add Apply Rollup Pattern, and click on our series reliability. We're going to keep these default boxes checked and hit OK. You can see that that creates those subsetted properties, which are now shown on the diagram here for each of our child objects recursively. And now if we click on that top level block and simulate that, you can see in our simulation window, we now have some values showing up in here. So if we expand a few of these and add values to our reliability properties, this REL, you can see our total reliability at the part 6, our total system rollup is changing as well. If we add a few more of these in, say part 5, give 0.95, you can see that number changes as we add these in, right? And we know part 4 is the rollup of parts 1, 2, and 3. So let's add some of those. And you can see that reliability value at our top level is changing with each value that we add here. From there, you can export these as a new set of instance specifications. You just click that button up in the simulation window and then select a package where you want to save those results. Then if you look in your containment tree, you'll see you've created a new set of instances that contain each of those reliability values. You can then use either a smart package, generic table, or an instance table to summarize these. In order to show these, I'm going to get rid of our old results, open up this table. I'm going to set my scope to the total package. This reliability column is actually a custom column I was using to show the slot value based on the property name reliability. Since we are now using the rollup method, I'm going to change that filter to show the total reliability. So just edit the custom column. You'll see I have a filter here, and we want to change the filter, which is looking at the slot name. And instead of reliability, we want that to be total REL. Hit OK. And there you have it. You can order this table so that you see the parts in order. We know part 6 is our total system. And we can see our new total system reliability is about 0.74. Thank you for watching this tutorial. I hope you found it helpful. Please let me know in the comments if you have any questions or suggestions for future videos, or reach out to me online. Thank you.